Thank you very much for the introduction. And this is Wen Guang. And today I will present my paper, Acoustic Imaging on a Mobile. The mobile-based imaging becomes more and more popular due to the prevalence of smartphone. And the most common way for it is to use a camera. But although the camera becomes increasingly powerful, it still lacks in darkness and under abstraction. RF-based imaging becomes an interesting alternative due to its capability to image through abstraction. However, existing approach cannot be supported by commercial smartphones and special hardware is needed. Also, its resolution is limited due to the fast signal propagation speed and the long wavelength. So in this work, we explore another alternative, which is acoustic imaging. And it complements camera-based imaging in following scenarios. First, it works under darkness and can be used to detect obstacles at road during night or in caves. Also, acoustic signals can penetrate many materials and can be used for underclosed weapon detection. Also, acoustic signals can propagate around the abstraction through diffraction or reflection. And we can use acoustic imaging to see objects behind the obstruction. Although acoustic imaging is very attractive, enabling it on mobile is very challenging. Traditionally, transducer array is used for acoustic imaging, and to achieve high resolution, the array size is large. However, large array is not available on a mobile. To solve this problem, we borrow the idea of synthetic aperture radar, or SAR for short. So to image a target, we only need one pair of speaker and microphone. We use speaker to send acoustic signals, which are reflected by target and received by microphone. And the key strategy here is to move the mobile by hand over a predefined trajectory to mimic a virtual sensor array. And we use the signals collected at all these locations to generate images. So to explain the key idea of SAR processing, we consider a single point reflector in the physical space. And by moving the mobile following a predefined trajectory, we collect the received signals and store them in a 2D matrix, S and K, where N is the index of smartphone position during the movement, and K is the index of received sample at each location. And after a series signal processing known as data formatting, the matrix S is transformed to I. Importantly, we note I is a 2D sinusoid. And by applying FFT, we will observe a spike in the frequency domain. So actually, the SAR processing is a mapping from the physical space to the frequency domain. And since this mapping is linear and one-to-one, so the shape of an object in the physical space will be preserved in the frequency domain of the received signals. This explains how SAR is used to generate an image. So when applying SAR to our context, we face some new challenges. First, speaker and microphone on smartphones are omnidirectional. So the received signals include not only the target reflection, but also the background interference. Also, it is hard to move a mobile by hand exactly following specific trajectory. Also, the speakers and microphones are not optimized for imaging purpose and introduce distortion on signals. All these factors will significantly degrade the imaging performance for SAR system. To solve these problems, we developed a new acoustic imaging system called AIM. It adds 3 new components to the SAR processing pipeline to remove the impact of interference, the deviation from the desired trajectory, and the speaker microphone distortion. In the following slides, I will explain the key ideas of these components. As mentioned, the received signals include not only the target reflection, but also the direct transmission from the speaker to microphone and the background reflections. We use a multipath channel model to describe the received signals, where X and Y are transmitted and received signals. TI is propagation delay, HI is channel taps. And since both X, Y are known, one way for interference cancellation is to use channel estimation techniques to derive the channel taps and then remove the terms with different propagation delay from the target reflection. Here, we assume we have a rough knowledge about the distance between the mobile and the target. However, since direct path signals is 1,000 times stronger than target and background reflection, directly applying channel estimation techniques result in degraded accuracies for these insignificant terms, which reduce the cancellation performance. To solve this problem, we develop a two-stage approach. In the first stage, we remove the direct path signals. And for this purpose, we record them in advance and subtract them from the received samples when we image on target. And also, we consider the automatic gain control on commercial smartphones, which automatically normalize the received samples and making the direct path signals scaling differently from recordings to recordings. To achieve best cancellation performance, we compensate this scaling difference when we subtract the direct path signal. After the first stage, cancellation, the residual direct path signal becomes comparable to target and background reflection. So we can apply channel estimation technique to derive channel taps and then remove the terms corresponding to direct transmission and background reflection. To evaluate the performance of our cancellation, we compared it with two classical methods: subtracting direct path signals without considering automatic gain control, and directly using channel estimation for cancellation. And we see our two-stage approach achieves the best cancellation performance. Next, we explain how we deal with the problem of hand jitters. SAR assumes the hand motion follows a predefined trajectory. However, it is hard to exactly follow it, and there are some motion errors. This changes the propagation delay of target reflection so that the received signals experience an actual phase shift, ME. Assuming the motion error at the nth position is given by delta n, then the phase error can be expressed by this formula. Based on it, if there is 1 millimeter motion error, we will get 0.6 radian phase error. Following figure shows an image of a point with different amount of phase errors. And we see when the phase error is greater than 0.4 radian, the image degradation becomes obvious. So to avoid this problem, we need to remove the phase errors. But however, existing phase correction algorithm for RF imaging radars cannot be applied to our system because special features of acoustic signals and the mobile setup. So in our paper, we developed a new algorithm to estimate and compensate the phase errors called MPGA. To explain how we estimate phase errors due to hand jitters, we consider a single point reflector, and with processing, the received signals, the phase of received signals can be decomposed into a linear, a constant, and a quadratic term. And when there are motion errors, we also have phase error terms. And for simplicity, we only consider the case column of sample matrix denoted by SK. And our strategy is using SK to estimate the last the sum of last two phase terms denoted by En, and then remove the quadratic term and derive the phase errors due to hand jitters. To estimate En, we apply FFT on Sk and find the maximum frequency component, which is close to omega k. And then we circularly shift the spectrum by omega and then apply FFT. Then the time domain signals becomes Sk tilde. And in fact, the previous procedures remove the linear phase term from Sk. And we take the derivative of Sk tilde and find the ratio between the derivative and Sk tilde gives the derivative of En. By integrating this ratio, we can estimate En. Next, we remove the quadratic term. And we achieve that based on following observation. The phase errors introduced by hand jitters exhibit a fluctuation pattern, while a quadratic term has a parabola pattern. So there's some En give the following patterns. And to remove the quadratic term, we fit En using a parabola and remove it from En. And this gives us an estimation of phase error ME, and then we can compensate its negative effect. So this figure shows an image of a bar using our system. Without MPGA, the image is severely distorted. And after using MPGA, we see the image becomes clear. Then we introduce how we deal with the distortion of speaker and microphone. So the frequency response of speakers and microphones is not flat at high frequencies. And this uneven frequency response introduces severe distortion of signals and blur the generated images. Following figure shows the image of a point, and we see because of distortion, the generated image is a blurred strip instead of a clean point. To remove the blur, we make the following observation. The blur pattern introduced by speaker and microphone distortion is deterministic because their frequency response is unchanged. So we can measure this frequency response and incorporate it in our simulation program to determine how the image of a single point is blurred due to the distortion. And we use a matrix R to describe this distortion effect. Once we know the distortion pattern of a single point, we decompose our object into a set of points, and each point is blurred in a similar way as described by matrix R. And the generated image is the superposition of all these blurred points. Since both R and I are known in our context, we can use them to solve the undistorted image, which is denoted by X. For this purpose, we use lasso regression to minimize the following expression. And the lasso regression not only removes the blur effect, but also reduces the noise in the image, because the regularization term prevents X from overfitting the noise pattern. Following figure shows the image of bar, and we see after applying focus algorithm, the blur is effectively removed. So for more technical details, please refer to our paper. To evaluate A, we implement a proof of concept system using commercial smartphones and image the cardboards with different shapes. And we see the images from the camera and our system match well. We also calculate the similarity between them using this expression where Si and Sg are object areas in two images, and Sc is their intersection. And we see the similarity values are high for different shapes, which indicates effectiveness of our system to capture the shape of the different objects. We also evaluate the performance of the imaging weapons, and we see our images can capture the outlines of the weapons. We also evaluate the imaging performance when weapons are put into the front pockets of the user's clothes. And we see without weapons, there is only some noise in the image. And when weapons are present, we see our images can capture the shapes of weapons. This indicates the potential of our system used for underclothes weapon detection. So here is a simple demo video for our system. Okay, that's very simple actually. Yeah. So recently, several imaging systems are developed based on imaging RF signals and acoustic signals, and they use different techniques such as non-coherent detection, FMCW, and beamforming. Also, they rely on different hardware such as 6 GHz transceiver, drones, array of sensors, and motion controllers. Differently, our system is based on SLR and only use commercial smartphones. In conclusion, we developed a smartphone-based imaging system in this paper, and our contribution includes a new phase error correction algorithm to remove the impact of hand jitters, approach to remove the blur effect due to speaker microphone distortion, and the acoustic imaging system implemented on commercial smartphone. For future work, we want to further improve the working range of our system and extend it to support 3D imaging. And also, we hope our work can inspire more interesting research about mobile acoustic imaging. That's all my presentation. Thanks very much for attention.